Maths channel. I'm now answering question number 4 from the May-June 2019. This is from the mechanics paper of Cambridge 9709, paper 4, variant 3. And we have a question here about connected particles and pulleys. And we are given this diagram. It says two particles A and B of masses 1.3 kilograms and 0.7 kilograms respectively are connected by a light inextensible string. So they're connected by a light inextensible string. So the word light, what does that imply? Now the word light implies that the string, we can ignore its mass. So we don't consider the weight of the string. And also it implies that the tension throughout the string is the same. Every section of the string, like the top part and the bottom part, they have the same tension in it. Okay, so that's the word light implies those two things. Inextensible means the string cannot be stretched. Okay, it cannot be stretched basically, right? So it's inextensible, which implies that all the particles attached to it will have the same acceleration. Okay, that's what that implies. Which passes over a smooth fixed pulley. Okay, so it's smooth, meaning there's no friction in it, which means the tension on either side of it will be the same. The tension on either side of the pulley will be the same. So the string on this side of the pulley and that side of the pulley will have the same tension. Fixed means it's fixed in place, it doesn't move. Okay, the actual pulley itself doesn't move, it's fixed in place. All right, particle A is 1.75 meters above the floor, and particle B is 1 meter above the floor as shown in the diagram. The system is released from rest with the string taut. Okay, the string taut means there's tension in the string. It's released, there's some tension in the string, it's not just loose. And the particles move vertically. So they move vertically. So A is going to move down, B is going to move up. When the particles are at the same height, the string breaks. So when they reach the same height, the string breaks. Show that before the string breaks, the magnitude of the acceleration of each particle is 3 meters per second squared, and find the tension in the string. Okay, so now I'm going to consider the forces acting upon A and the forces acting upon B, and then we're going to work out what we have to work out, which is the magnitude of the acceleration, and show that the acceleration is 3 meters per second, and also find the tension in the string. So there is the weight of the particles acting downwards. Always the weight acts down. And the weight is the mass times g. So this is going to be 1.3 g. I'll leave it in terms of g for now. And this is 0.7 g. And we have the tension in the string, which acts upwards. Okay, in both cases here. But the acceleration of each particle, okay, is in opposite directions. So the particle A is going to accelerate downwards. The particle B is going to have the same acceleration in terms of its magnitude, but it's going to accelerate upwards. Okay, so if we consider the forces and the resultant force on each particle, we know the resultant force is equal to the mass times acceleration. Okay, so if we consider the particle A, it's moving down. Okay, so we're going to take down as positive. And the resultant force on this is going to be 1.3 g minus t. As going down, we're taking down as positive. So it's going to be 1.3 g minus t, and that's equal to the mass, which is 1.3 times acceleration, which we have to show is 3 in the end. Okay, so that's one equation we formed from the situation by considering A. Now, if we consider B, very similar kind of situation, except this time it's moving up, so I'm going to take up as positive. Okay, so for A I'm taking down as positive, for B I'm taking up as positive. Why? Because B is moving upwards. So in this case, the resultant force, if I'm taking up as positive, you've got T is positive and 0.7 g is negative. So you have T minus 0.7 g is equal to the mass, which is 0.7 times A. Don't put 0.7 g, don't put 1.3 g here for the mass times acceleration. We just want the mass times acceleration. This is the weight. Okay, so we have these two equations which we can solve simultaneously very easily. we can eliminate the t from the equation by adding the two equations together. If we have equation 1 plus equation 2, we're going to basically, these two will cancel out, minus t plus t0. We have 1.3g plus minus 0.7g, which is going to give you, I'll just write it out, so showing our steps. Okay, and you have 1.3a plus, remember we're adding the two, plus 0.7a, which is 2a. Okay, so that's going to give you 1.3 minus 0.7, which is going to give you 0.6g equals 2a. So a is going to be 0.6 over 2g. So that's going to be 0.3g. And as we take g as 10 in Cambridge, this is going to be 3 meters per second squared. So there's the answer to the first part of this question. This is two parts. It says should find the acceleration. And then it says and find the tension. And find the tension. So don't neglect to read the question properly. Some people just say, show that the magnitude of acceleration is 3, and they just forget about the rest of the question. There's two things we have to do here. The second thing is find the tension, which is pretty simple because we have here, one of these two equations we can use. Let's use equation 2. We know that a is equal to 3 meters per second squared. So t is going to be 0.7a plus 0.7g. So t is going to be 0.7 times 3 plus 0.7 times 10. So that's going to be 2.1 plus 7, which gives you 9.1 newtons. Okay, so there's the answer to part A. Okay, now for part B of the question. Okay, now for part B. So part 2 of this question, sorry. So now they're told to find the difference in times that it takes the particles to hit the ground. So basically, the important thing here is for us to realize from part 1 of the question is that when the particles are at the same height, the string breaks. So when they get to the same level, the string will break. Now, when will they get to the same level, or what is the situation when they get to the same level? Well, that's going to be when basically A and B have both moved the same distance. Okay, A has moved down and B has moved up. They move the same distance, and it's this distance between them in the beginning divided by 2, basically, right? So if we take the distance between them and divide that by 2, so the distance between them would be this distance over here, okay, which is basically 1.7 minus 1. And we divide that by 2. So we have 1.75, minus 1 and divided by 2. That will give us the distance between them, or the distance that they, A moves down and B moves up when that brings them to the same level. Okay, so A moves that distance down and B moves that same distance up, okay, which will be exactly the half of the distance between them in the start of the journey. And that will tell you how much A moves down and B moves up. Okay, so that's what we have to do. So we're going to have 1.75 minus 1 divided by 2, which gives us 0.375. So we have 0.375 meters. Okay, so that's the distance that A moves down and B moves up. So I'll just put it like this. That's going to be 0.375 meters, and this is 0.375 meters. Now, what do we know about them before the string breaks? Okay, so before the string breaks, what do we know about them? Before the string breaks. Excuse my handwriting here. Well, we know that A is moving down or accelerating downwards with the acceleration of 3 meters per second squared, as we found in part A, and B is accelerating upwards with an acceleration of the same 3 meters per second squared, but upwards. Okay, so same magnitude, just different direction. So B is accelerating upwards 3 meters per second squared. All right, now, so let's try to find out at the point where they reach the same level, okay, what will be their situation. So we're going to have A going from there to there, from this level to that level. What's going to be the situation of A when it reaches this level? Okay, so when it reaches this level, okay, let's call this level X. Okay, let's say for A to get to X. All right, for A to get to X, okay, at that, from where it starts from to get to X, what's going to be the situation? Well, let's use suvat. Now, by the way, the speed that A reaches when it reaches this level and the speed that B reaches when it reaches that level, they'll be the same speed because they're collected by the same light and extensible string. So if I work out the velocity of A, okay, so the velocity of A, we can say at X, velocity of A is equal to velocity of B, okay, before the string breaks, all right? So that's because they're connected by the same light and extensible string. So if I find the velocity of A, I find the velocity of B. So from A to X, if we use suvat because they are, it's constant acceleration, which we found earlier. So S, now A to X, it's moving down. The initial movement is down. So down is positive. So it's going down 0.375. So that's going to be positive because it's moving through that distance downwards. Okay, its initial speed is 0 because they were released from rest in the beginning, as I mentioned in the beginning of the question. V is what I'm trying to find, the velocity of A at X. A is the acceleration, which is down as well, so that's going to be positive 3. And the time it takes for it to reach this point, we don't really need to know that for now. Okay, you can just leave that as it is. So here we got S, U, V, and A. So we can use V squared equals U squared plus 2AS. So we can say the velocity of A squared, which we're trying to find, is U squared, which is 0 squared, plus 2 times A, which is 3 times 0.375. So let's see what that gives us. We're going to have 2 times 3 times 0.375. That gives us 9 over 4, which is 2.25. The square root of 9 over 4 is 3 over 2. So basically, you're going to end up with the velocity of A is going to be 1.5 meters per second. It's a nice, easy number. The square root will give us something difficult. So that's the velocity of A at X. Okay, this is at X. So the velocity of A and the velocity of B are both 1.5 meters per second at the point when they reach X before the string breaks. Okay, they have the same magnitude of velocity. Okay, magnitude. Okay, but A is going up, so A is going down at this point. A is going down and B is going up with a velocity of 1.5 meters per second. Okay, now what we're going to do here, there's different ways now we can work it. We want to work out the time it took for A and B to reach the ground. We find the time it took for A to reach the ground and the time it takes for B to reach the ground, and then find the difference between them. We'll answer the question. All right, so there's two ways we could do this. Okay, we could, from this point onwards, so it says find the difference between the times. So the time it takes for A to reach this point and B to reach that point is the same. Right, so that's fine. Okay, that's what we're dealing with here. Right, we don't really need to find that because we know they're the same, and the distance between them will be 0. So what we've got to find is the difference it takes between A to reach the ground. So A is falling downwards. So if you find the time it takes A to reach the ground from this point down here, after the string has broken now, where now there's no tension in the string. So we're only dealing now with its acceleration due to gravity. After the string breaks, basically the magnitude of the acceleration is going to be 10. Okay, it's going to be G basically, right? So therefore, it's not going to be the same situation. We have to use different equations, different values for suvat, right? Now, but B is going to be moving upwards. So it's going to go up. It's going to come to rest. And it's going to start falling down. And then it's going to hit the ground. So there's two ways we could deal with this. We could work out the time it takes for A to hit the ground by using the value of, its displacement from the ground. We could work that out, which is going to be 1.75 minus 0.375. Okay. And we could work out, using suvat, the time it takes for A to reach the ground. And we can do the same for B, okay, from this point upwards, okay, which will be basically 1.375 from the ground. And, how long it takes for it to go from here to there and then down again until it hits the ground, right? Now, I think the easiest way for us to deal with this is as follows. Because I know that when B basically is falling down, okay, so B is going to go up and then it's going to come down again. Now, the point it's going to come down again, okay, its speed is going to be the same speed with which it was going up, because at this point, the string broke, it was going at this speed, right? And now the acceleration due to gravity will be the same. The acceleration will be just due to gravity. So when it reaches back down to this level, it's going to be going at the same speed, but downwards, okay, at the same level. So its speed on the way down will be 1.5 meters per second going downwards. And the time it takes for A to reach the ground and B to reach the ground after B has gone up and then down again will be the same. Okay, because it's going to be going down at 1.5 meters per second at that point, and it's the same distance as falling because they're starting from that same level. And, the time it takes for B to reach the ground and A to reach the ground will be the same after B has gone up and then it's coming down again. So the difference between the two times will be the time it takes for B to go up to its highest point and then down to the same level again. All right. So what we can do here to make life easy for ourselves is we can consider that, let's consider for B from X back to X again. Okay, it makes it very easy then. So B, okay, let me put this over here so it looks different. So B is going up. Okay, it's going upwards with the speed of 1.5 meters per second. And then it's going to go up and then down again. And it's going to be going down at 1.5 meters per second. But this time it's going to be going downwards. So this would be like negative, you could say, right? So basically, if we consider B from X back to X again. It's going up and then down. Okay, let's look at what we have. We have suvat. Now, its displacement between this point back to this point is going to be 0. I'm talking about displacement from where it started at this point. Its initial speed is going to be 1.5 meters per second squared. Its final speed is going to be minus 1.5 meters per second squared. Acceleration is going to be, we're taking up as positive because it starts off, this is like its initial, speed. So we always take the direction of the initial speed as the direction that we're taking. So it's positive, up is positive. So the acceleration is down, so it's going to be minus 10. And this is the time we're looking for. All right. So we can very easily here use V equals U plus AT. Makes it very, very easy then. So minus 1.5 is equal to 1.5 plus minus 10 times T. So you're going to subtract 1.5 from both sides. So minus 3 equals minus 10T. So T is going to be minus 3 divided by minus 10, which is going to be 0.3 seconds. Now that's a very, very easy way of dealing with it, right? But you have to just understand a few things. That at the point when B reaches X, before the string breaks, it's going at a speed of 1.5 meters per second upwards. Okay. And then, the time and then as it's going down, all right, as it's going down, it's also going to be going at a speed of 1.5 meters per second but it's going to be going downwards, right? Which is the same speed with which A fell to the ground from this same point. So the time it takes A to reach the ground and B to reach the ground once B has reached this point on the way down will be the same. So all we need to do, the difference between the two times, with the time it took for B to go up to its height, its maximum height, and then down back to here again, which we can use this, displacement for, because we know that on the way up, the speed is 1.5 meters per second. At the same point on the way down, it should be the same speed, right? Because it's going through acceleration due to gravity. It will be the same level, going at the same speed, but in the opposite direction going down, right? So we worked out what the speed of A is when it fell this much, which is the same speed that B was going to be moving at when it rose this much, as the strings were connected, or the string wasn't broken. At this point, the string broke, so B was like thrust upwards with a speed of 1.5 meters, came to rest, and then as it fell down, it came back to this level. It's going down with the same speed that it was rising. It's only acceleration due to gravity. So if I can work out the time it took for B to go from up here to down here, that will be the extra time that B took to fall to the ground. Because from this point, once B is moving down, it's the same situation as A. Right, so that's a nice, easy way of answering this question. We could have done what here? Sorry, a bit tired now. What we could have done was we could have worked out the time it took for A from this point onwards until it hit the ground, okay, by using suvat, v squared equals u squared plus 2as, I guess. S equals ut plus a half at squared. And we could have done the same for this from this point, upwards and then downwards. And then the difference of the two times, we'd have quadratic equations to solve. And the difference of the two times would be our time. But this is way easier. Now, I did mention in the beginning, I'll show you an alternative way of answering part A, I think. No, answering this question. Answering this question. There's an alternative way we could answer this question using, I think, work energy principle. All right. So I'm going to, what I'll do, I'll save that as a separate video. So that way, that would be under a different kind of chapter heading or different playlist. So I'll tackle the same question, part 2, using the work energy principle in another video, okay, which will be the same playlist as this paper. So other questions from this particular paper you can find in the playlist that will appear on the top right of the screen at the end of this video. Other questions from the topic of connected particles you can find in the playlist over here, and suvat in this question, in this particular constant acceleration playlist over here. You can subscribe to my channel by clicking on this link. Thank you for watching and see you soon.